This is Mrs. O'Neill for AP Chemistry, Chapter 7, Section 5, Electron Affinities. So we talked about ionization energy already, and ionization energy is the amount of energy needed to remove an electron from an atom, or remove the second electron from an ion. However, what do you think electron affinities is then compared to ionization energy? Hopefully you guessed it. It's the energy released when an electron is added to an atom. So it's the opposite of ionization energy. So here's the difference. Again, I suggest you pause the video, fill in the blanks, and then play to hear my words. So if we look at this example for chlorine, and we want to remember, look at this, we're still in the gas phases. So we want to remember that. Ionization energy is amount of energy needed to remove. Look at this, it's a positive 1251 kilojoules per mole. I know it says delta E here for energy, but this should also remind you of delta H, enthalpy. And if it's a positive, that should make sense. How much energy is needed to remove? So how much energy is needed to break those electrons away from that chlorine atom? So if we think about that reaction diagram, this is the part that's endothermic, the part that's going up, the part that's breaking those bonds, the part that is spreading apart those IMFs. Electron affinity then is the opposite, is how much energy is released when an electron is added. So notice our delta E really resembles delta H. It's a negative sense, and it should be negative because we're bringing things closer together. We're bringing the chlorine atom, adding an electron, and then getting that chlorine negative charge or ion. So it's coming down in that energy diagram, right? It's that exothermic part where we're bringing things closer together or making bonds. So then why does the electron affinity for chlorine have less energy? So here we have an atom of chlorine gas, and we're changing it to a chlorine plus and plus electron. So that's our ionization energy. And that's a plus 1251. So that's going to take a lot more energy than the opposite, or the electron affinity of chlorine. So if we take chlorine and we're going to add an electron to it, it becomes chlorine negative. Okay, so it's negative. I understand the positive negative, right? We're breaking, we're forming endo, exo. But this is only 350 kilojoules of energy versus the 1251. So why do you think that is? Hopefully you can understand that, of course, it's easier for chlorine to gain electrons than it is to lose it. So for chlorine to become an anion, it's much easier for that to happen. So, of course, the amount of energy needed is going to be less than actually taking it away. So here again are the difference is between ionization energy and electron affinity. And what would be the trend? Well, in general, the electron affinity increases from left to right as the kernel charge increases. So again, the amount of electrons and protons. From the bottom to the top, because there are fewer electron shells, allowing those valence electrons to get closer to the nucleus. So again, I always think about trends in a diagonal sense. So it's very similar to ionization energy, but should make sense. You're going to have a small amount here because we're giving it away, and we're going to have a large electron affinity here because it wants to gain. So here we want to lose electrons, here we want to gain electrons. So it's very similar to electronegativity and ionization energy, but it's a little bit different as far as the reasons. Now, let's see if you understand this. I'm just going to kind of go through these slides. It's a quickie quiz for yourself to make sure we're understanding up to this point. Read the question, pause the video, see if you can come up with an answer, and then play the answer. Okay, so hopefully if you still have questions or not understanding, hopefully you can bring them into class and ask them. Otherwise, a lot of this stuff, again, goes back to that Coulomb's law and the attraction between those protons and electrons and how many energy levels the atom has. Okay.